Hello, everyone. Thank you so much for coming to this workshop number 2, part of the ML Ops Micro Summit, focusing on the Bay Area. If you have any questions, please free to ask them in the chat on the right-hand side. Just a quick note: we are going to be starting the talks at 5:30. We're also going to be hosting community mic at 5 o'clock. So please feel free to join. I'm just going to hand over the mic to Elle for the workshop.
All right, thank you for the intro. Hi, everybody. I'm really happy to be here today talking to you all. I've done a couple of talks, with the ML Ops conference before, and it's always been a really great time, and it's a really cool set of people, great interest, great questions. So I'm going to do a bit of a short talk and then some hands-on coding today. And what we're going to be talking about is GitHub Actions and using them for data science. And so I'm going to say, feel free to ask questions, put them in the chat as I go. When I'm doing live coding, I'll do my best to answer your questions as I see them, because sometimes I think like it helps, I don't know, if I do something on the screen that doesn't make sense, it really helps to get an answer quickly. So I will do my best to keep up with whatever questions you have. But I'm going to just start with some slides to kind of introduce the problem that we're working on here. All right, setting up my screen share. Okay, so here we go. Okay. So we're talking about how to automate machine learning with GitHub Actions. Now, first, a little bit about myself, and that's that for most of the last decade, I've worked in academic research in various areas of neuroscience. And one constant in my work is that I've always used a lot of very big computers, and I always do a lot of mathematical modeling. And when I got my PhD last November from the University of Washington, I was interested in how scientists in academia and industry use computers and how we're going to build tools that enable high quality science as our methods and our data sets and our problems all get more complex. So I joined this company Iterative as a data scientist, and our flagship project that you may have heard of is called Data Version Control, or DVC for short. This is our little owl. And in fact, we have a real life rainbow owl mascot, DV, who is just the most adorable mascot and about 15% of why I joined. Not really, but maybe. Anyway, DVC is a tool that adapts version control systems that software engineers are familiar with to machine learning projects. And specifically, it helps us extend Git version control to work better with some of the large file types, that we need in data science, like big data sets, big binary model files. So you can still use Git, and DVC is not a replacement for Git. It works with Git. Anyway, that's a little, what is DVC? So as an organization, we live at the intersection of data science and DevOps. And so what I'm going to share is kind of one of our newer projects. Okay. So I want to start to set up this problem with a figure from this case study that I really love. It's a study of teams all across Microsoft. For 2019, and the authors reported that teams, whether they worked on speech or search or ads, all tended to follow a very similar workflow on software projects that involved machine learning. And of course, there are a whole bunch of folks with different skill sets working on this. We've got data engineers collecting, cleaning, and labeling data. Data scientists are engineering features, then training and evaluating models. And software engineers are deploying and monitoring applications built around those models. And this is my dream company run entirely by baby animals. Anyway, everything is fine if the project proceeds linearly, passing off from data engineer to scientist to engineer like a relay race. And of course, that almost never really happens. So we know that excellent machine learning models rely on feedback, right? If you just put, a model up, it's probably stale within a month or two. Assuming that your data set, is changing over time. Most data sets in the real world I've encountered are not super stationary. So software engineers and data scientists might have to pass modeling experiments back and forth. Data scientists need to be able to anticipate the system constraints of software engineers who will deploy their models. When we can't do this, we end up with problems where, the model that worked beautifully on my desktop doesn't work for anybody else and completely isn't compatible with with the system that we actually have in production. And everybody needs to know where exactly the data came from. And so there's a lot of back and forth, right? So the process is not linear. It is highly not linear. There's a lot of recursive loops here. And all of this can get extremely confusing very quickly. And machine learning is a new part of the software engineering workflows, and it's not always easy to incorporate. But luckily for us, software engineering isn't a new discipline, and we can learn a lot from the field's evolution. And specifically, DevOps has had success bringing together developers and operations specialists. So we are kind of hopeful that, the DevOps revolution can be maybe an inspiration for how engineers and data scientists can find ways to work together too. So one of the big ideas from DevOps, which has really changed the way that multidisciplinary teams run, is continuous integration and continuous delivery. And we abbreviate that CI/CD. So CI/CD is a practice that establishes collaboration rules between developers and operations specialists. So let's look at what that means. When you make a change in your source code, a build happens automatically, and then some test gets run on that code. And if the build passes the test, the modified source code becomes a candidate to be merged into the main branch of your project. And the idea is that every action, like a Git commit, will trigger feedback, and every round of feedback produces a release candidate. So here we've got this loop: change your code, build, run some tests automatically. If you fail, you keep iterating. If you pass, then this is a candidate to be deployed. So let's take a look at what's different when machine learning is part of the workflow. A few things. First off, it's not enough just to monitor our code. We also need to monitor for changes in our data set, because in machine learning, if your data set changes, that can have a huge effect on, what the resulting model looks like. And in most applications, I'd say data is more important than your code. Next, it's not just building software, you're training models, and that can be both resource and time intensive depending on the type of model. Even a lot of scikit-learn models are really not trivial. If you've ever had to do a huge matrix factorization and your CPU just can't handle it, it happens, even when you're not going into deep learning. Another issue is evaluating model is not quite the same as running these pass-fail tests. So what does it mean for a model to pass, right? We can create some kind of thresholds, okay, just don't be worse on accuracy. But, model performance is nonlinear, and it has to be understood, kind of in different segments of your data. It's very possible for your overall model accuracy to go up, but something like precision to get worse. And if that's acceptable really depends on your application and your domain. So I'm going to say that most of the time, a binary evaluation of your model is going to be not enough info to decide if you want to deploy a model. So we need more detailed reporting, some model metrics, maybe even some data viz, and it has to be inspected by, a domain expert like your data scientist. So there's a few reasons why it's not trivial to just kind of snap on all the things I talked about into existing CI/CD systems. First off, version control can't always track changes in data sets. If you've got, a lot of data sets that we work with, you don't want to Git version them. So you don't want to wait for there to be a Git diff, in your data set in order for your CI/CD loop to trigger. Another issue is that training models isn't like building software, right? We've got some, potentially specialized hardware, some driver needs here if you've ever tried to set up CUDA. And evaluating metrics is just more complicated. So the pass-fail tests that we have, which we're used to, are probably not going to cut it if we want to have confidence in the models that we're, sending out into the world. So what we think is needed are tools that extend CI/CD practices from the domain of software engineering to machine learning. And this is something that we're thinking about as we continue to develop DVC. So we make tools. We're going to give, a shot at extending CI/CD systems to work better for data science and machine learning. So I'm going to show a wish list for some of the features that we might want if CI/CD will work for ML. So first, we want to be able to version data like code. We want our CI system to be able to allocate whatever hardware is needed to train models. And we want metrics about model performance to be reported in a human readable format so data scientists and other team members can easily review them. And so the work I'm going to be sharing today is a collaboration between myself, David Ortega, a developer, and Dmitry Petrov, who's the CEO of our org and DVC creator. And so the tools that we're going to be working with, right? So we as a team, we love developing in the Git ecosystem. So DVC works with Git and GitHub and GitLab and Bitbucket, any kind of Git repository hosting system. And so we are looking at these really cool continuous integration systems in the Git ecosystem, specifically GitHub Actions and GitLab CI/CD. As of like a week ago, we actually did add Bitbucket pipelines to this too. I just didn't update the slide. But anyway, just know that that's there too. So these services, what they do is they provide a continuous integration system that's quite easy to use. It's got a pretty low barrier to entry, I think. And there's a tremendous overlap in what you can do with GitHub Actions and GitLab CI. So for the most part in this talk, I'm going to focus on kind of GitHub Actions use cases, but just know that everything I'm showing you actually works for both of these. And right now we're working on Bitbucket support too. So our project, we have an open source project called Continuous Machine Learning, and a few ways that you can follow it. We have this website, cml.dev, and we have a GitHub repo, and the GitHub repo is kind of like the hub of the project, right? It's where all the activity is. And so to explain a bit about how, GitHub Actions can fit into your workflow, if we were to revisit this figure, GitHub Actions can help us with this part of the CI process. So things like automating model training and testing. So GitHub Actions is a service that runs a workflow that you define every time a triggering event happens, like a change is pushed to the project repository. And by default, GitHub completely orchestrates, getting a machine that will run your workflow with the right operating system. And if you specified a container, it'll have the container, it'll run it and then report back what happened, give you all the logs. So, you can use your own machines too, instead of kind of GitHub's computers, and we'll revisit that in a bit. But basically just to kind of summarize where you can see GitHub Actions fitting into this loop. And if it's not clear, because I do think that continuous integration is a little bit hard to understand if you haven't actually seen it. So I will be jumping into this in live coding soon. And hopefully if you're not really sure what I'm talking about, which I would not be surprised about, that's how it felt to me when people were describing this before I saw it. Seeing it in action, I think will kind of help you close the loop in your head about it. So I want to share kind of how we've handled hitting our wish list. So to take us through the priorities that we'd laid out, one of them is that we wanted to be able to provide feedback in the form of metric reports. And so the way that GitHub Actions works is that you will take basically you put this special file in your GitHub repository. It's always going to be a YAML file in the path.github/workflows. And it's got a syntax, kind of like a standardized format for of different fields that you'll be looking for, or that GitHub will be looking for. And you can define things like triggers. So you can say, I want this workflow to run on push actions. You can pick a Docker container. It can be yours, could be ours, just, you can, and it's optional. You don't have to use it. And And then you can specify a workflow, something like, I want to run this Python job. So I want to install my requirements and then run train.py. And then finally, we've created some functions as part of the CML project to help you write things like text, tables, and images into a Markdown report. And then we can help you deliver that Markdown report into your pull request. So when you get a pull request in GitHub, you can have data viz, numbers, text. You can actually put any kind of file in, and if it's not supported by GitHub Markdown, we'll just display a link and host it for you. So you can put like an audio file or a video, and it'll just give you a link. The basic idea then is that when you make a PR, you get a report with whatever details you think are important to have. And so then, hopefully your whole team can inspect this. So to take a closer look at what's in the workflow, we have a training script that outputs a text file of metrics and a confusion matrix in this little sample that I have here. And we do some bash scripting with our helper functions to add the reported model accuracy and confusion matrix to the report. And we deliver it to your pull request with this function CML send comment. And here's another example where I'm using DVC to make a table that compares model performance metrics. So one of the things that DVC does is you can do things like, I'm going to make a diff in terms of model metrics, right? So it's like you can often do git diffs and get line diffs. But in data science, you might want what's a git diff on a huge binary model file? We're going to do maybe a diff on model metrics. So what was the accuracy of the model in these different commits or different branches? So this is showing how I've got a pull request. And what I'm doing is I'm using DVC to create a metrics diff comparing metrics on the, my branch that I've got the pull request for and the main branch. And I can report that table here. And I can also plot the loss functions from the two different branches together. And this is using Vega Light plots. DVC plots is just a wrapper for Vega Light plots. And we have another case where, we wrote a little wrapper function so you can stick a tensor board in your link. And so pretty much you can make this work with any kind of, service that you like. So I'm pretty confident, we're working on some integrations coming up soon for, a lot of other data set and model monitoring tools that people like using. So if you have an integration that you're interested in, just open up a ticket on our GitHub repo and let us know. Tickets are a way of voting for the features you want us to make you. Anyway, the big picture here is that we made these reports as customizable Markdown documents, and they're super flexible. So you can put whatever you want in them, right? Like I'm just showing you putting PNG files basically into, the Markdown report. And that means that you can use whatever visualization library you prefer. It could be Seaborn or ggplot or Vega or whatever. We try to make it pretty agnostic. And likewise, any way of writing a table too. You can write HTML tables. You can write, any way you want it pretty much. And that means any language too. So you can do R workflows, Python workflows. Nobody's tried Kotlin yet that I know of, but Anyway, so kind of to give a sense for like, okay, well, what would you use this for? These kind of reports. There's a few ways that we see these reports fitting into a workflow. One could be a report about model training on remote machines. So you could use the remote machines in the CI system to train your model in response to a push, and then report back things, details about the training or performance of the trained model and some validation set. You can also just focus on model testing. So you could develop the model locally on, you could experiment, try lots of different models on your own machine using whatever experiment tracker you like, and then check in your favorite model into your continuous integration system. You git commit your favorite model and push it. And then you can use continuous integration to run some standardized tests, basically. So maybe take the model, put it in a standardized Docker container and check that it runs, check that the inference time is acceptable. If you have a couple of kind of benchmark data sets, try it out on those and report the results in your pull request. So you don't have to do model training at all in the CI system. You could just do it for testing as well. And finally, you can review data sets and models like code. So you can also use the pull request to kind of be a way of comparing a change in your data set and get, maybe a CML report about how your data set has changed from whatever is on the main branch. And we have a video series going here, shameless plug. We have a video series. Last, when I presented this, it had 17K views. I think it's got more than that now. But we have a video series on YouTube full of all sorts of tutorials and use cases where, we're kind of learning what people want to see, and then making tutorials about it. All right. And I'm going to get to the coding pretty soon, but just kind of to tie this in, mention what are the other things that we did. We wanted to version data like code. And so we've added support to using data version control, DVC, in GitHub Actions. So it's kind of like you can just have DVC ready to go on your action. And that means that you can do things like add and push large data sets. So DVC, not an alternative to Git or a replacement. It works with Git. So if you had a data set or like a trained model file that's prohibitively large for hosting on GitHub, you would track it with DVC. And then the syntax is going to be similar to Git. And what happens when you push is that you pick whatever kind of cloud storage you like to be your data remote, and then DVC coordinates sending a copy of your data to that remote. So on your local machine, the way it works is that DVC creates a lightweight metadata file that can be tracked with Git. And this lightweight file is what goes in your GitHub repository. And so this sample file contains a hash. The hash indexes the version of the data set as well as its location in cloud storage. And then you can use GitHub Actions and kind of this method that we made to pass some of your credentials to the workflow, which you can store as secrets. In GitLab, these would be called variables. And in this way, you can have a workflow that will pull data. So when you pull data, you're going, okay, go from my cloud repository, which could be like your S3 bucket, your GCP bucket. It can actually be Google Drive too. Grab my data set and put it onto the runner that I have right now running this workflow. And then when I'm ready to push, I can go from the workflow and I can take a model and put it in the cloud. And this means that your GitHub Actions, your runner can work with data sets that are too big to keep in GitHub, and it can, save models that are too big to keep in GitHub. So some consequences, when you use DVC, changes in your data set can trigger your GitHub Actions, even if the data set isn't Git tracked. So the way that would work is, right, you have this lightweight metadata file. When your data set changes, you would kind of use DVC to go, hey, my data set changed. And then that will change the file, the metadata file that's being versioned by Git. So that file will change in your GitHub repository, and that will trigger your GitHub action, even though the data set itself does not reside in your GitHub repository. Now GitHub Actions can push and pull big artifacts to cloud storage. There are other ways to do this too, with things like, you can always do like wget or curl and point to, a bucket, but then you'll have like these kind of nasty hard-coded links, and DVC pull and push give you a nice high-level abstraction. I think that is a lot easier to read in a workflow file and a lot less brittle. And data and model versions will be linked to every model training run. And because you can use like S3, you're not using a server for your data. And so, you can use whatever serverless storage you like, or you can use a server. It's up to you. All right, and finally, the last thing that I wanted to touch on was how can we get our CI system to allocate cloud resources to train models? So far, everything I've talked about is using, kind of the computers that come with GitHub, GitHub Actions, and they're tiny. There's not going to be any GPU on them. And in fact, you can hook up your actions to run on other machines. It's quite easy to do this for like your own GPUs or your own compute or your EC2 instances. But we're working on a workflow, and actually what I have here with Docker machine is what we have right now on our project, but we are replacing it with a Terraform system, and it's not done yet. So I'm not going to talk about all the gory details of it, but basically what happens now, and what we will have a new and honestly even cooler method for in a few weeks, is basically you can push to initiate training in the cloud. And by that, I mean that you can push and then GitHub Actions will provision a computer that, maybe with the GPU, like your EC2 GPU machine, it will turn it on. The EC2 GPU will run your job, and then it will turn off at the end. So you don't have to, have like your GPU machine on listening for jobs. It will be turned on by GitHub Actions. It's super cool and super fun, and it lets you do cool things like you can train a style transfer model on your GPU. This is just kind of an example that we did, and so I'm just comparing how the style transfer looks on the main branch of the project versus this experimental branch, and in response to changing some parameters. And the cool part about this is that you don't have to remember to turn your cloud GPU on and off. You don't have to like boot them up and interactively modify your code on your machine before training. You can modify the code from anywhere, and as soon as the change is pushed, the CI system will take over and start your instance. So to kind of sum up all of the big ideas here for our project, we wanted to version data like code, and DVC extends Git version control to data sets. So that's how we're getting around this issue. We want our CI system to allocate cloud resources to train models. And not only can you set up your own machines to be like listening for jobs, which is kind of a basic built-in feature of both GitHub Actions and GitLab CI, but you can also deploy cloud resources from GitHub Actions. And finally, we wanted to be able to provide feedback in the form of metric reports. And so we've got some helper functions for writing reports in a pull request. And so we're pretty excited about this because we think that CI/CD systems make a lot of sense for machine learning projects. They're a way to bring together your training data, your source code, and modeling experiments all in one place. And that gives everybody on your team access to all versions of the project, including history and ongoing experiments. And it provides a standardized format for storing and sharing any kind of files related to the project. So I have now told you all about how cool I think this is. So let's just do some coding. So like I said, if you get questions while I'm showing this, just feel free to ask in the chat. So I have made this kind of repo here just for this. It's a toy problem. I'm going to show you the general, a general workflow, something that you can do. And so I'm not going to get into the data management or cloud compute provisioning aspects here. This is a toy problem basically with a data set that fits inside your GitHub repo. I'm really just going to show off some of the value that you can get for a data science project from doing CI/CD to display interesting data viz and reports about your model. So I got this wine quality data set where we have all these properties of wines and then quality ratings of the wine. It seems like a classic Kaggle problem. I've got a script that creates a model. So what it does is we're going to load in our data, do a train test split, and we're going to fit a random forest regressor. Let's see, and I'm going to write some metrics out to a text file. It's just a regular, boring old text file. And then I'm going to make some plots of feature importance. So we've got, you know, just different, this is just a thing you can do in random forest, plot the feature importance. It's kind of nice because it's a little interpretable. And then I'm going to do a residuals plot, so a scatter plot of residuals. I've got a requirements file. So these are the, you know, some of the libraries that I need. And this is my project directory. So if I were going to add workflow file, what we're going to do is we're going to do add file, create new file, .github. It's always in the same directory, /workflows. And we can call this whatever we want. So train and report.yaml. Okay, and there's a pretty typical file format. So for that, I'm going to go to the CML repo and I'm going to just grab a template that we have. So you can just go to our repo and we've got this kind of standard format. And I'm just going to copy this much. Okay, so I'm going to train and report. I'm going to say set a trigger and I'm going to say on push. And then our job is going to run on an Ubuntu container, on an Ubuntu machine. And we're going to pull our Docker container. And just note that we are, you know, we're going to be actually unveiling something in like a few weeks too, that you don't have to use our Docker container. And actually you don't have to use our Docker container now. You can install the CML library with NPM if you want. And that is just fine, especially if your org has, you know, your own custom Docker containers. So I'm going to do it this way because that's kind of the simplest way to show this for now until our GitHub Actions come out that you install easy and CML more modularly. But just know that you do not have to use our Docker container. And then we're going to do these steps. So this is kind of a typical GitHub Actions standard. You want to check out the current repository, and then I'm going to do this stage here. And let's see, train the model. And let's see, I'm going to use this repo token. So repo token is basically access credentials so that GitHub Actions can write comments to your pull request, and you don't actually have to provide a secret. So you can just ignore this line if this means nothing to you. It's fine. It has to be there, but you don't have to think about it. Okay, and now our workflow goes here. So I know for sure we want to do pip install requirements, right? So we want our requirements to be installed every time. Let's see, and then I'm going to do Python, and I think it's train.py, Python train.py. And now I'm just going by memory, but I know that this train.py is going to output metrics.txt, feature importance.txt, and right, this is a PNG. And residuals.png. So just keep that in mind. So first what I'm going to do is add text. So I will do echo metrics, and I'm going to create a new file called report.md. So this is just some bash scripting, and I want this to be like a header in the report. And then I will just do cat metrics.txt. So dump the contents of metrics.txt into report. Now let's do add pictures. Echo data viz and echo feature importance.png. All right, feature importance into report.md. And now I'm going to use a special CML function to publish this feature importance.png image. It goes CML publish feature importance.png, so path to the file. I'm going to do this flag for Markdown. I want to specify that we want this formatted for Markdown, and then I'll put it into the file. And now let's do echo residuals. You don't have to do as many headers as I do. I just think they're pretty. And you don't have to do it in bash scripting either. You could write this report in a Python script. Now I'll do CML publish residuals.png, then markdown flag, dump it in the report. And the last thing we'll do is send the report. So we'll use CML send comment report.md. Okay, so we had these files that we wanted to kind of report the contents of, our metrics, our feature importance bar chart, and our residuals, and we have dumped the metrics. We have published our feature importance image and placed it in the file, and the same for our residuals. So I'll just remove this for readability, and I'm going to create a new branch for this. I'm going to do, just call it workflow. And here we go. When I make this commit and pull request, all right, let's see what happens. Let's see. So now we're waiting, and we can see that we have this queue here. So we've got a job running, right? We can tell it's running. If I go to details, and what we're seeing is inside your, the machine. It's just like getting a look at the logs from inside the machine. So we're grabbing the container, and this is usually the longest step. And there are things you can do, like there's caching with GitHub Actions, and I haven't set it up. It's a little bit more advanced, but there are definitely ways to get the time down on container pulls. And I haven't really done them here. So the size of, the amount of time it takes is just dependent on what you're pulling. And let's see. And of course, like even the fastest jobs are not going to be as fast as like running on your computer. Like if I had just changed something in my, my model training script on my local computer and just do like python train.py, that is going to be faster than running this. So I kind of think of this as like while you can do development here, I tend to think of this as maybe like a second stage, that first you can do rapid iterations on your own workspace. And then when you want to start testing, you can check your models or your code in here, and then you can have like a suite of tests that you want to run or reporting, because it is going to take more time. So it's not really a replacement to the kind of, rapid iteration you can do on your super lightweight, laptop. It's just, you avoid the problems of like, it doesn't run anywhere off of my machine, right? You're testing in really standardized and completely reproducible environments. So now we're training, and if we look in here, we can see that we were doing all of the pip installs. If you have really predictable, Python package dependencies, you could put them in your container too. Anyway, here we go. So here we are. We ran our job, it worked, no error message. Okay. So the job is done. And now if I go back to my pull request, we can see it. Here we go. So our metrics, training variance explained, test variance explained, and we've got our graph of feature importances here. Cool, okay. Our residuals are here. All right, and then, we could decide if we wanted to merge this or not. So let's make another change. So if I go back to the code, and let's go on to this branch here, and let's change something. Let's see. I want to know what the returns are for going even deeper. So maybe I'll go, well, I feel like that'll take a while. How about, how good can I do with a very shallow model? I'll just decrease the depth and see what happens. Let's see. Okay, I changed it. Here we go. Commit on this branch. Now we wait on the pull request and we can see we've got the yellow dot. It is running. All right, so now we're just waiting. We can see here, it's just running. Another view you can get is from the actions dashboard, and that'll show you the list of actions you've done and what branches they were on. So it's just going. While we wait, any questions on what I'm showing you so far? Waiting for it to run is a great moment for questions. And I see Manoj, I hope I said your name right. Thank you. Thank you for stopping by after seeing YouTube videos. I'm just pulling up some other kinds of projects that I have here. Yeah, when this one is done, I'm going to show you one of my favorite kind of, I don't know, reports that you can do. It's about behavioral testing of machine learning models, and I think it's really cool. Any questions? I'm sure somebody's got a question or a comment. Another really nice thing about this is it builds some waiting in your day. So you can wait for your models to test and go get a coffee, and it counts as work. It's like getting compile time in your day. All right, okay, so this job ran, we got the check mark, and GitHub Actions will let you know if it didn't work with an incredibly disheartening big red X that will ruin your day. So if we go back to here, we can now look at this commit and we can see things generally got a lot worse. So we really, I would not be super happy with shrinking the model and getting these results. And we can see that when we shrank it, it's not using most of the features at all. So that's not great. So I probably would not want to merge this in its current state. But the cool thing you can do is that when you get these reports, you can always go back to exactly what was the state of the project at that time. So you can go to the commit, and you can look here, and you can always browse the repository at this moment in time and figure out, what were all of the files like. So you can know exactly what requirements did I have, what was my workflow. So your versioning, your data set, your model, your environment, your code, and the infrastructure that you ran it on. So in this way, I think it's pretty thorough. A question here, can DVC CML integrator work with MLflow, or are they mutually exclusive? Yes, they can work together. So I feel like MLflow does a really good job with experiment tracking, and some teams really like that. And so you can do your kind of developing experiments, on MLflow, on your machine, and then you could take a model and then check it into your, GitHub or GitLab repository and run a bunch of automated tests on it in this way. And then you'll have it like tested with your containers, and it's easy to share, right? Once something is in continuous integration and in your GitHub repository, it's very easy to share with other teammates. So that's kind of an advantage for doing this. So you can absolutely pair up. I'm going to do something like MLflow, or, there's any of the kind of experiment, monitoring suites with this for, doing continuous integration. DVC, you can also use for pushing and pulling things to cloud storage. So kind of the main difference between, I think, DVC and CML and something like MLflow is I feel like MLflow is definitely going for being an end-to-end platform, so that you can do everything from experimenting to deploying, and all of that within this one platform. And I think that we take a fairly different approach, which is DVC and CML are kind of modular. They're meant to be used in stacks that you create. So kind of by design, it's totally okay if you just use CML reports and you don't use DVC at all for the experiment tracking or model storage. like that's up to you. We'd be happy if you just use CML for reports in your pull request. So they're kind of modular tools, and we're not trying to impose like a stack on you. You can pick, you know, everything else to do with your continuous integration system. So that's kind of our philosophy. And we are working on some integration so that you can have like, you know, I saw somebody did this with Neptune ML recently. Like you can put, you know, a Neptune kind of report. I'm not sure exactly what it is, but it was like a report generated by Neptune, and you could put that, you know, with CML. So there's lots of ways to cross them over. And I'm sure that as we develop this, and especially once we have the DVC and CML GitHub Actions, which are super modular, it will get easier than ever to combine them with whatever tools you're already using. All right, now I'm going to show you just kind of one of my favorite examples. So this is a repository called Typo Test. And what it is that we're going to check how robust a sentiment classifier is to random typos in our data set. And we're going to report this test. We're going to do it automatically whenever we change our code or our model or our data set. And we're going to then automatically test, you know, how robust is our latest model to typos, and report the result in our pull request with some failure modes. So to unpack what this means, here's the test. If you're given a sentence like, "I just love the new Honda I bought from Crystal," we could introduce a random typo to get this sentence A prime. So like here, we'll just have a typo. And what we want to find out is, does our sentiment classifier give the same answer for both of these versions of the sentence? So generally, adding this typo here, you know, should not seriously alter, you know, the estimation of the sentiment of this sentence. And we can do this kind of perturbation over hundreds or thousands of example sentences, and then estimate what percentage of examples, you know, is the classifier robust to that perturbation. So just to be clear, the task is positive or negative sentiment, and ideally a classifier would still, you know, label these both as positive, even when there's some random typos present. Generally a good kind of feature to have. So I've got a data set. Again, I'm just doing the data here, which is not best practiced, but it is for the purpose of illustrating the testing capability. So I wanted to make this super replicable. So we've got a data set full of, you know, there was used car dealer Yelp reviews in Seattle. So there's going to be quite a lot of fiercely negative feelings in there. And I've got a script that will run perturbation test. So what I'm going to do, I'm using the Hugging Face model library. And what I'm doing is I'm grabbing a model. So I've got Albert base, you know, this is the model that I have right now on the main branch. And then I'm taking data from my, you know, that big list of sentences, and I'm randomly perturbing each sentence and then comparing, you know, on average, how many times does my classifier get the same answer for the perturbed in the original sentence in my test set. And I print out, you know, I care about the percent, what percent of the time is the classifier robust to typos. And I also want to write out like really interesting failure modes. So what are some examples where the model is very confidently gives a different answer once a typo is present? So I've got a score and I've got some failure mode examples. And so what I can do on a pull request, for example, so I made a pull request where I switched the model. I switched it from an Albert to a Distilbert model. And again, none of these models are stored in the GitHub repository. These models are part of the Hugging Face Model Hub. So at runtime, the runner will use, you know, the Hugging Face API to pull those models into the workspace. So you don't have to keep the models inside your GitHub repository. And so what I'm doing is I'm printing out, you know, how the scores has changed on the current branch and the main branch. So the main branch has Albert, the current branch has Distilbert, and I can print out the diff in the accuracy. So not a huge change at all. So that might give me confidence that, you know, it's, even though the accuracy got slightly worse on this perturbation test, it's really a % I could live with. So I wouldn't consider this a huge regression. And if the Distilbert model is smaller than Albert, that might be a very good reason to make this merge. And then I've got these failure modes here. So I can see that this sentence, this was the original "such an inspiring car," and this was how it looked after some random typos were inserted, and that the classifier had said now this was positive and this was negative. But I find that quite understandable. I don't know if I would know what this means. You know, some of these, I test drove it, it ran good. I test drove it, it ran booed. I might think that's negative. This one I find kind of odd. The sales department is about as helpful, knowledgeable, and straightforward as I've ever seen at a car dealership, and all that is about to Z-bout. I guess I find that a little suspect. And this typo here, I find that kind of odd. So I might go in and look at that a little bit further. I don't know. I'm not an NLP specialist. This was something that, you know, kind of an approach that I learned from, there's an ACL paper, like award-winning paper about an NLP checklist that came out this year that kind of prescribed like a list of tests that you can run kind of to create a checklist of NLP models and how they're performing. And this is kind of based on them that they suggested testing, you know, for perturbations, how it affects the model when there are random typos, so robustness. And so this was just an example of, I made one of these tests and I want to report it, and presumably you could have like a whole suite of tests, you know, to verify on your you know, your NLP model, and make sure that when you change something in your pipeline or your modeling approach or your data set, you're not getting a huge regression on one of those tests. And then when you're happy, you can merge the pull request, and I probably would merge that. All right, so I think that that's everything I was going to show you today. So I think let's just move to some questions and discussion. Cool. I see a question from Rahul. Happy that you have large dataset versioning functionality in DVC. We have our CSV dataset stored in a S3 data lake, partitioning by certain columns and applying compression per partition. Can you configure DVC to store retrieve dataset in a partitioned way in the cloud backend of your choice? I'm not sure, but I don't see why not, because DVC is pretty agnostic to format. Yeah, I think so. You know, this would be a good question to go into. We have a Discord channel, you know, and if there was any reason why you would have issues with that, with compression, then I'm sure somebody there would spot it. So I would say you can check out our Discord channel and ask there, and our dev team would be able to know for sure if there's anything, but my thought is that is fine. One thing about data lakes, though, is that DVC, just to know, it depends on the scale of your data lake. So DVC is best for files that will go in your workspace. So kind of to think about it, like if you have like terabytes and terabytes of data, DVC is probably not ideal for that. It's made more for like, I have like a model file, like a binary model file that's like 2 gigabytes or something that's going to, you know, I would normally have this in my workspace some of the time. So DVC is really designed for data that will pass through your workspace because it's actively being used by data scientists. So it might be like, you know, this is the, you know, a data set that, you know, I use today, and it can live in my workspace. If you're at the scale of like, it always has to be read out of a huge database, and the database is on the order of like terabytes and terabytes, there are definitely, I think, better tools for operating at that scale. So we're really good for things on the order of like, you know, 100 megabytes, anything just too big for GitHub to like a few hundred gigabytes, I think. So just keep that in mind when thinking about data lakes. Any other questions? Thanks. Anything else? If anybody's using GitHub Actions already, I'm definitely curious. Thanks, everyone. Thank you. I thank you, and DV thanks you. My emotional support owl here. And just a reminder, like all of this is an open source project. So we're pretty much always interested in, feedback, input of any kind. Our repository is the place to go. Open an issue if anything does not work for you. If you want to use this on your workflow, but it does not fit for whatever reason, like if it's not compatible with your CI system or something, like just let us know, and that's really good, and we'll try to work on some support for it. Another question, what are some things you're excited to add to CML and DVC in the future? I am really most excited about the cloud computing and provisioning. It feels amazing to like make a pull request from my laptop and then it like turns on a GPU in Ohio and then turns off at the end. Like, I love that. And I love not having to like interactively log on and, configure, machines. I think that it doesn't really make sense to me that like I'd have to interactively, engage with like all of the EC2 instances that I want to run in order, just to use them as compute power. And so I feel like I'm quite excited about, how we're using Terraform. It's just like the coolest feeling. Oh yeah, let me show you. So we've got this YouTube channel and it is the place to go. This is my personal YouTube channel here. Let's see. Yes, we have a YouTube channel. Here we go, DVC.org. This is it. You could be our 2000th subscriber. It could be you. There's no prize, but it could be you. And so what we've got are all these tutorials based on MLOps. And so these are just, some of what I've covered today. There's a lot more. So we've got things about like how to set up using your own GPU. I've got like the typo test as a video. I had a chat recently with the data scientist, Jeremy Jordan, all about like going really deep into how should behavioral testing look. We're pretty hopeful about behavioral testing kind of being, an important part of ML model testing in the future. We've got the no code explainer, and then we've also got basics kind of to cover like all of the DVC docs. So the DVC docs are now almost entirely matched with videos. So if you don't like reading, you can listen or watch. So we try to come out with a video like every week or two, and they are highly driven by things that people ask for. So we definitely, any requests are super welcome. So yeah, so come on by. All right. I think that's everything that I have today. So Faraz, should we call it a day?
Yes. Thank you so much for a very great presentation. Thank you so much for once again for coming back on again as well. And also thanks to all the attendees at the workshop. Once again, we will be sharing the videos as well as the slides after the summit. And we look forward to welcoming you back at 5 o'clock for the kickoff for the talks. Thank you so much. Thanks, Elle.
Thanks, everyone. Bye.